Well, it's a great pleasure to introduce Leonardo Krapp, who is currently a 51 Pegasus B fellow here at the University of Arizona. We managed to convince him to come here a few years before that, and he's been doing some really phenomenal work on planet-disk interaction. He's also effectively a skilled applied mathematician and has done some phenomenal algorithm development to create some of the world's best codes to study all sorts of problems with multiple fluids on both GPUs and CPUs. And I think he's going to tell us about some of that exciting work today.
Yeah. All right. Thank you. Thank you, Caitlin, for the introduction, and thank you to the organizers of the Origin seminars for the invitation. I hope you can hear me well soon, and yeah, otherwise just put a comment in the chat. I can speak a bit louder. I don't know how this works actually, but yeah. So I would like to talk about some of the recent progress that we have done here together with Caitlin and some other collaborators, trying to understand a little bit more about planet formation in the context of computational astrophysics and three-dimensional models of planet-disk interaction. I'll try to let you know why this is important and where we're going now in terms of advancing some of the perhaps leading theory to explain planet formation, but also trying to make contact with different types of observations and whether we can improve our forward modeling, and also we can have some power for the predicting power for future detections with the current instruments, so on. So I guess to begin with, we'll start with a plot that probably is very common for the audience of the Origin seminar, which is the Exoplanet Demographics results and the legacy from Kepler. I think it's never bad to emphasize how important is this data and how we drive the theory also from some of these results and how it's changing the paradigm of how we understand planet formation. Among the many biases that are behind these results, there are some broad things that I think there's some good degree of consensus, and it has to be with the fact that gaseous planets are ubiquitous. We look at planets there with gaseous atmosphere, so that is telling us something about the formation history. Presumably, to get the gas, they need to form while they are well embedded in the gaseous disk. And the other results that we have, which I think is one of the best things from the Kepler legacy, is that if we now look at the solar type star in the neighborhood of our galaxy, it's very likely that we will find there a super Earth type of planet, or sometimes they're being called mini Neptune. There's some minor difference there, but and that type of planet is not in our solar system. So our solar that put our solar system in the kind of on a rare size of the planet architecture that we detect in our galaxy. So we need to understand why, and we're trying to make some progress to understand which type of processes are crucial there to explain why super Earth's short periods planet with gaseous envelope more masses than the Earth form, and they never became a gas giant, for example. So what prevented them to keep accreting to become a gas giant? And so there are many important physical processes there, and one of the leading theories that we use still today to explain the process of planet formation and how the atmosphere came into place is the Krapp accretion theory that goes back to Mizuno et al. From the early 80s, and then the great work from Polak et al. In 1996. These are one-dimensional models that combine a lot of physics and trying to understand different regimes of planet formation, of accretion, or different regimes of accretions that go from a solid, the core that is growing and accreting slowly accreting gas to the point that it will eventually reach a runaway phase of growth and becomes a gas giant. These are one-dimensional models. There's many assumptions behind it. There has been a lot of progress as well in recent years with these one-dimensional models. But we have to keep in mind that these planets are not isolated. Planets do not form in isolation. And even in this one-dimensional model, some of the effects of this can be taken into account. That is not a trivial task, because planet-disk interaction is indeed a non-trivial problem. There's a lot of physics and dynamics there that can change the flow of gas and solids from the disk to the planet. Different effects that can drive planet migration, instabilities. There's a lot. I don't have the time to go into all the diversity of physics that is there, but we have to think that the planet is well embedded in this, and the flow of the disk can penetrate into the well inside the accretion zones of the planet, of the growing planet, and change the properties of the growing process. So there has been some progress, especially in the last decade, trying to make a connection between the 1D models that can take into account a large integration in large time scale, and three-dimensional models that are very complicated, computationally expensive. We can only integrate a few orbits, but still we can make some connections. Not every time, and not all the physics can be cast from 3D models into 1D models. And in this talk, I will show yet another non-trivial process or non-trivial scenario that we have now in three-dimensional models that may also challenge some of the one-dimensional pure accretion model. We have to advance a bit more to have a more conclusive answer to that. So some of the standard or well-known works from the last decade that shows that three-dimensional models are definitely showing that there is an anisotropic distribution of accretion and material, and the flow topology is quite complicated. So to put all this into a 1D model is not trivial. It's not an easy step, and we need to acknowledge all this process. The accretion is anisotropic. There is a lot of flow coming from the protoplanetary disk to the inner part of the core, changing or the entropy distribution, changing the amount of heat, preventing the core to cool. There's a lot of recycling of material that can prevent the cooling of the gas and stop the accretion or slow down the accretion. The combination of magnetic field and gas can also drive a lot of non-trivial dynamics, polar outflows, redistribution of angular momentum, and so on, and many other examples. But one of the common themes of all this work, perhaps, that was missing, which is the main point of this talk, is the distribution of solids in these simulations. So if you want to look at the dust, how is the dust being distributed here? And what is the important consequences of distribution? So that was the work that we did last year, and we are still working on in new results that I would like to show at the very end if I have some time. Solids are important for, I guess, many reasons. I will highlight 3 reasons that I think are the backbone of planet formation. It has to be with accretion. So dust and solids represents 1% of the total mass of the disk, but still they control all the process of planet growth, which has to be with how much material, solid material you accrete to form the core. And in recent years, the theory had advanced from the accretion of planetesimals, so forming a core from kilometer-sized body, to also include the accretion of pebbles, centimeter-sized or order of that particles, and they can also increase the amount of solids and make the growth process faster by order of magnitude. Not just the accretion, the other important process is the cooling. So solids regulates the opacity. These systems are cooled. The main source of opacity there are grain sizes. And if you change the distribution of solids, you change the opacity. And if you enrich your gas with solids, you can also slow down process like runaway accretion. And this has been an alternative explanation also for the super Earth distribution that we have in the exoplanet demographics. Not a few, but almost a decade ago, So we don't only care about how planet grows and the local thermodynamics, how the gas cool down, but also we care about where are the planet in the disk. So the other backbone of planet formation is planet migration. And it has been very nice work, perhaps a bit overlooked, in my opinion, in the last years, but very interesting result from Pablo Benítez, who is now a professor at the Universidad Adolfo Ibáñez in Chile. And he has shown, to the best of my knowledge, for the first time, and in a systematic way, that if you include the dynamics of solids, and if you care about low mass planet, you're talking about cores of few Earth and Earth masses, or few Earth masses, so the first early or the early stages of planet formation. If you include the effects of solids in the dynamics, you can change the migration history, to the point that you can revert the type 1 inward migration and have an outward migration, for example, in some cases. So this is a plot showing a torque density map, comparing the effect of the torque, the dust on the torque relative to the gas, relative to the torque sucked by the gas component. And whatever is blue here indicates either a slowdown or reverse migration. This is something that we need to pay more attention now. We have the tools to work this out, and we are learning and discovering new physics just from including dust in our simulations. This is not a trivial task, including dust in our simulation, especially if you want to include the distribution of sizes. Things becomes very expensive, computationally prohibited very rapidly if you want to go to 3D models. So along with the astrophysical results that I'm going to show today, I also want to show how do we deal with this problem of almost impossible to perform this type of simulations, and how can we do a characterization or a better characterization of the three-dimensional distribution of solids in our models by improving as well the way we deal with differential equations in computational astrophysics. To begin with, we want to consider the distribution of sizes, different grain sizes that exchange momentum with the gas component. And we want to model that balance for different type of distributions. We can think about the power law. The important thing is that we need to solve a set of nonlinear differential equations. And the more beams we use to characterize our particle size distribution, the more expensive this becomes, because we need to solve the hydrodynamics of tens to hundreds of fluids all together, exchanging momentum at the same time, self-consistently. And one of the major drawbacks is that this system of equation is a stiff system of equations. So there are many different time scales combined, and it's a bit challenging to solve, especially if you want to add the momentum exchange between the species. So what we did together with Pablo was to develop a new method that take the advantage of the system being stiff, and we use some operator splitting techniques, combined like standard hydro techniques, and develop a new method to solve the momentum exchange between gas and dust that get rid of one of the most constrained things of the simulation, which is the time step, the stability constraints of the simulation. So we developed a new method that is unconditionally stable, and that improves the efficiency. If you look at this plot here, I have any pointer, but I can maybe point with my cursor. This is the computational cost of a standard standard drag force solver that takes into account the solution of this equation with respect to the hydrodynamic. And as you increase the number of fluids, number of species, it rapidly dominates, and you cannot, you need a very large amount of resources to make progress. So with the new method, we essentially remove that cost, and we also add a new level of parallelization now, because as Kevin mentioned, this code also runs on GPUs, and now we can put different fluids in different GPUs and get the dynamics simultaneously. And we are also advancing this. This solution is very efficient, but it's first order in time. Now we have a second order in time, so we have a not only unconditionally stable but more accurate solution. And we are working now with the student, Juan Garrido, who is here now visiting us. And he's also in the job market, so he's looking for a PhD position. If you want to talk to him, he's going to be here until February 22. And we're almost finishing the second order solver that can also be coupled with a different type of hydro solvers called Riemann solver. For those who are interested in that, we can talk more at the end. But all that combined in the Fargo 3D code allow us to present perhaps the first generation of multifluary three-dimensional simulation of planet embedded disks. So what type of physics can we study with these techniques? So this is one example. Here we're going to look into the dynamics of the global disk. So full 2-pi azimuthal standard disk with a low mass planet embedded there, and 11 different sizes. That's species that we see there. They all have a different degree of settling. We are looking at the slice of the disk that is midplane to the upper atmosphere, and we see that the smaller species are less settled than the larger species that are more settled towards the midplane and at the bottom of the plot. They have an equilibrium scale height that is defined by the parameter H delta, and is defined as HD here. It's a function of the pressure scale of the gas. And it's a free parameter in the simulation that we can change. And the idea is that we then start to run these simulations with different planet masses, different settling parameters, and trying to understand how the dust distribution change into this, and what is the final outcome of this interaction. And this is very challenging, and as we're gonna emphasize it towards to the end again, because this is a multi-scale problem. The scale of the planet, the bondiosphere of the heliosphere of the planet, where the planet gravity, if you want to simplify in that, put it in that terms, the planet gravity tries to dominate the dynamics with respect to the gravity of the central object. Is a much smaller scale than the scale of the disk, but still, the flow is perturbing the global scale. The planet excites spiral waves, opening gaps. There's a horseshoe flow all across and along the disk that we need to resolve, because that circulates towards and inside this scale. So the resolution is pretty demanding here to get the multi-scale problem with a reasonable or adequate resolution, right? And this is a snapshot of the small portion of the disk with the integrated dust density, where you can see the large-scale spirals that the planet excites in the dust. Dust grains are being lifted above the equilibrium density there, above the equilibrium scale height there. And also you can see the bondiosphere of the planet, and you can see that the dust density there already is non-isotropic, non-homogeneous distributed with respect to the gas. This is, you see these spirals being triggered there that increase the amount of dust relative to the background. And these are tracing the velocity, the gas perturbations. Presumably, we have the momentum exchange between the dust and the gas, but the main outcome is that if you look at the semisphere here, of bonded hemisphere, you see that the spiral wedge introduces asymmetries. And there is a latitudinal gradient and there is a symmetry gradient. So we already brought the 1D spherical symmetry that we are using in the core accretion model, just by looking careful at the dynamics here. And this is what happened for different sizes. If you look for smaller sizes on the top, larger sizes at the bottom, this is showing the relative density with respect to the gas. The gas is spherically, symmetrically distributed. The gas is in a local hydrostatic equilibrium with the potential. So a 1D spherical symmetric approximation for the gas is actually not a crazy idea, but you see the gas is breaking that because it has some settling with respect to the central potential, but also that settling, that latitudinal gradient that we see here is being enhanced by the planet potential. And So we are actually not seeing any steering. The planet potential is not steering, it's not lifting grains everywhere. It's just enhancing the gradient towards the midplane, increasing the latitudinal gradient. And this can happen for different parameters. Here we're looking at different settling conditions, more settling here, less settling here. We have different planet masses here and here. And overall, we see that the asymmetry persists. It's being enhanced, of course, if you go towards stronger settling, but it is there. It's a ubiquitous result from these systems. And this is just highlighting that gradient in a different plot, so that this plot corresponds to average, azimuthally average integrated plot along this azimuthal coordinates. But I'm just reinforcing what it has say. This asymmetry being persistent. So we are looking at the dust distribution there, and one thing that we can wonder is about the opacity distribution. So now we have these dust grains there that may regulate the local thermodynamic of the system. So what about the opacity distribution? So we take the different grains. These are all sizes. Again, at the top, we have smaller sizes, micron sizes. At the bottom, we have something like centimeter sizes for this system. And then we can calculate the opacity, or at least the mean opacities. So using some monochromatic opacities based on standard mean theory calculations, we can get the Planck mean opacity and the Rosland mean opacity, which are very important for the thermodynamic of the gas. And look at the distribution of that opacity now. And we see that the asymmetry is still in the opacity distribution, not only just in the dust density. You can think that when you average the dust density with the opacity, then you wash out that asymmetries, but that's not the case. And an important parameter that determines the gradient, or is a proxy for that gradient that we see in the opacity from the midplane to the polarization of the envelope bond sphere, is the settling equilibrium of 100 microns to 500 microns grain. And if that settling equilibrium is smaller than the bond sphere of the planet, you will start to see stronger gradients to perhaps order of magnitudes from the midplane to the polarizations. And that can have some implications for the thermodynamics of the system. And we're trying to understand that now. The important thing is that you still see that gradient in the opacity. And you can translate that gradient now into, for example, a mean-free path, right? You want to know, well, you have this opacity gradient, but what else is telling me about the local thermodynamics there? And if you translate that into a mean-free path, you can essentially get different regimes that are optically thick and optically thin regimes, where you expect different thermodynamics dominating both regimes. And you see that in some of these models, when we did that conversion, we actually get that the planet envelope, the bond sphere, the planet, is optically thick near the midplane and is becoming optically thin above the midplane as you go to the polar regions of that envelope. And this is an asymmetry distribution that depends on the latitude potentially, or colatitude. So it's not trivial to cast in a 1D model, a spherical symmetric accretion model, because by definition, those models do not take into account any gradient that's not on the radial direction. So this is a challenge now, and we also, but I guess before making the connection, the final connection between the 1D and the finite models, we still need to investigate further the implications for the thermodynamics, because in those simulations, we still don't have the planet feedback included, the radiation from the planet there. We don't have that temperature distribution, and we don't have a proper treatment of thermodynamics there. So before going back to the beginning and making that connection, we need to keep investigating, improving more our models. We need to go step by step. We first put that there, and now what we're doing now is trying to through the radiative transfer there, and that's when I'm going to be expanding the last part of my talk, just highlighting a few results. This is a summary of the first part, which is essentially telling that this multifluid global simulation is showing asymmetries in the dust distribution at the scale of the bondiosphere or inside the bondiosphere of subthermal planets, which we believe may be the course for giant planets eventually below, if you want a number, 10 Earth masses, roughly speaking. So I guess I can take maybe a question, or I can just continue and move to the second part of the talk, which is of course connected to the first one. But,
maybe a really quick one about how the computational cost scaled with the number of fluids involved. I was just wondering why it seemed that there is a bump and then it goes down again, even though you increase the number of fluids. And that thought that you showed.
Yeah, so at the beginning, because the scale of the standard solver is going from something like n squared to n cubed as you increase the number of fluids. So you shouldn't see like a perfect scaling, but it's changing. And that has to be with the cost of how you invert the matrix, or sort of an implicit problem, or a linear problem, basically. But let's say n is the number of fluids, your cost will go from n to n squared to n cubed as you keep increasing. And the transition between those regimes is non-obvious, depends on the system that you have sometimes. I guess the important fact is that we now remove all that scaling, and the system now scales linearly with the number of fluids. So more fluids, the cost of the simulation will increase proportional to them. Before that, we will be increasing with the power of the cube of the number of fluids. So we want an n squared there. At least, yeah.
Yeah, I'm curious about the computational time of one model you run, and will it be possible to compare the real observation data with any of these opacity models?
That's the second part of it. Thank you. Thank you for the introduction. So with that, we move to next generation of planet-based models. And now we're going to move from core accretion theory or connection with core accretion theory to connection with observations that we have from protoplanetary disks. We have many, and this is of course probably known for all of you or many of you, the part of the D-Shark legacy observations. We see millimeter size grains there, a lot of substructure gaps, rings, spiral arms. And we still are missing the protoplanets. At least in the majority of the cases, we don't have a clear indication of the presence of a protoplanet, at least from the emission. We can infer that, but careful, because the standard approach to infer now the presence of a planet is taking isothermal simulations, studying the dynamics, painting some dust there, and doing the post-processing radiative transfer, and comparing with the data. But in those steps, we break some consistency because the temperature of the local thermodynamics of the system is being modified. So maybe that's not a big deal, but maybe it is. And there was a work by Leonardo a few years ago showing for very simple cases and simple simulations, what happened when you abandon the isothermal equation of state, the local isothermal equation of state for the simulations, and you go to a different regime when you have radiative damping or radiative cooling on a thermal realization time scale. And if you look at the perturbations on the planet exerts on the disk, these spiral waves, they are clearly being damped for some of these regimes, where beta here is a parameter that tells you about the time scale of radiative damping for different conditions. So if you go from local isothermal to non-local isothermal, you can see strong damping in those features. And if you now put some dust there and look at the synthetic observations, you can get a zoo of discrepancies here. The problem is very degenerate. It's very hard to say something that is convincing, at least to my eyes. And in this figure, there's a lot of information. So there's not only the inclusion of radiative damping of different temperature regimes, there's also inclusion of different viscosities, background densities, surface densities, and temperatures. But there's also inclusion of different opacities, just to highlight one of these plots here. So you go from a ring to maybe two rings just by changing the opacity. So we are now, a bit running into problems because things start to become more degenerate. And how do we explain these observations? We can infer a planet mass that generate this in an isothermal disk, but also we can generate two rings if you change the mass. But now, if you go to a different regime, non-isothermal, you can get similar results with complete different settings. So yeah, a warning flag here, I guess. But how do we still want to make progress. We still want to say something about the observations. So the way I would like to make progress now, and I think Caitlin will agree with that, is that we need to abandon the isothermal or local isothermal equation of state for radiation hydrodynamics. And we need to consider the dust dynamics there and the dust distribution there to set the opacities, because these anisotropies that I just show you. So we're working on that. These are new models where we have a radiative transfer solver. So before, the system of equation was just the block here to my very left. Now we need to add the radiative transfer, at least with the flux limit diffusion, still strong approximation, but definitely a bit more realistic than a local isothermal in some cases, to some extent. And well, the ultimate goal, if you get the non-ideal effects, there are magnetohydrodynamics. I'm not going to talk about this, but I'm definitely interested in that as well. So how do we do it? Because this was already expensive. Well, we find this new solver for the dust. We make it work. Now we are adding the radiative transfer, much more expensive. And you have to keep in mind that there are at least two important scales that we want to solve. The scale of the planet envelope, the Hill radius, and the global scale of the Horseshoe region that goes all, along the planet orbit. So we need at least two resolutions are very well defined, and that sets the constraints in our simulation, how expensive they can be. So again, we need to improve the way we solve the equations. When we do theory in computational and astrophysics, our daily basis job is to find new, more efficient and accurate solutions for a system of partial differential equations. It's not just running simulations, but sometimes it is. But so we have, this is something I'm very excited about, a new method, a new solution to these differential equations. And I would put it in these terms. The Fargo method, I will explain the details of this now, but the Fargo method is perhaps the most useful numerical method that we have for the computational of disk and planet with this in the last 20 years or so. It's been a very powerful method because it improves your accuracy and improves your efficiency by order of magnitude. I will explain why. The strongest limitation of the Fargo method is that can only be applied to a certain type of grids. It has to be uniform. Your spacing has to be uniform along one direction. That's a strong limitation. If you wanna do these simulations, you wanna have non-uniform grids distribution, right? So you wanna have very small grids near the planet and increase the size of the grids as you go away from the planet. So then, we couldn't do this Fargo method. We couldn't apply Fargo method anymore, and I was feeling that we can do some better. So I called Pablo Benitez Shambai is the main developer of Fargo 3D. He's very talented, very skilled, and I told him we need to do something with this. We need to improve the advection here, and we did it. And hopefully, we will get the paper out this week or the next one. And as I say, we have two scales, one near the planet and one far away from the planet. As a resolution is still expensive, but we need to start looking for places that we can gain something. And orbital advection is one of that. So orbital advection is essentially the advection of the flow along the azimuthal direction here. And that is limited by Keplerian rotation. And the way to understand that in simple words is that if you look at the simple advection equation that's part of the hydrodynamic here, you need to advect the quantity Q here with the velocity B. And that velocity B can be split into a bulk velocity, Keplerian rotation and some perturbations. And if you solve this numerically, the methods, standard methods, have a constraint on the stability, which has to be that the size of your time step in the hydrodynamics has to be limited by this condition, current condition, whereas the size of your cells divided by the total velocity and the sound speed here. So if your bulk velocity is much larger than the velocity perturbation of that sound speed, this time step decreases a lot. But we know that the bulk velocity is a Keplerian velocity, so we can take advantage of that and try to remove it by splitting the equations. So this is a technique called operator splitting technique. We just split this equation into two and combine the solutions to get one solution. It's a very standard numerical method. And the way we do it is that the first equation we now solve it analytically because it's a linear advection equation with B0, so the solution just shifts. The non-trivial part is doing the shift in non-uniform methods and conserving the mass, conserving the momentum. So doing that, finding that analytical solution in a conservative form, that's non-trivial, that's part of the paper, but still is the analytical solution. And for the second one, we use the same method as before, but now without the bulk velocity, we remove that constraint and the time step increases significantly. That means we can integrate more time step with the same resources. And if you look at the speed ups measurements, they go from a factor of a few up to almost 2 orders of magnitude with respect to standard methods to solve the same problem. So again, we are winning some efficiency here. This is problem dependent. This method may not necessarily apply in terms of efficiency to all the problems, but for this type of problem, we are finding that it does really help, does really improve and reduce the computational cost. So now we have the radiative transfer there, the multifluary gas species. We recover the anisotropic opacity distribution. Here I'm showing a test case, a global disk with an embedded planet, different planet masses. And on the top, I'm showing the opacity distribution for these two cases. And even now that we have a different thermal equation there of energy, a different thermodynamics, we still see the anisotropic in the opacity, so that's persistent there. And it has to be with the fact that opacity is mainly driven by gravitational forces and drag forces, so not that by the local temperature distribution. And we also show, going back to the question as well as the question before, at the bottom we show extinction maps. So we now are calculating extinctions from the simulation, trying to understand what type of feature of signatures we can detect, for example, with ALMA, or observations like that. So is this shaking or?
It was shaking, yeah. Somebody's doing something up there.
Not an earthquake, but it's something shaking here. All right, thanks. What was I passing out? All right, so so perhaps the final message is that we now can do radiative transfer with dust. This may remove the need of post-processing in terms of comparing simulation with observations, but that's a very delicate step because one other thing that we are missing here, and we are trying to investigate now with Caitlin as well, is the local thermodynamical equilibrium, because in this radiative transfer approximation, we still have the assumption that gas temperature is the same as gas temperature. That may break, that can break down as well. So you have a different temperature for different grains. That can drive some hydrodynamics for the future. But this needs to be calibrated with, for example, tools like RANMC. We are doing that now. And from that, I think we will have more confidence in the type of predictions and the type of forward modeling that we're going to do with this vast and diverse zoo of observation of protoplanetarities that we have ahead. So with that, I wanted to thank you, and yeah, happy to take more questions if we have time.
You hear that great talk. Are there any questions online or in the room?
You mentioned you are using non-LTE mode for the radiative transfer, but my understanding of the disk is mostly very abundant. I mean, the number density is pretty high. So what will be the difference if you just use the LTE instead of non-LTE?
So it's a good point. So if you look at the alteration of the disk, and if you look above the midplane as well, you start to see some strong deviation from the LTE, and you need to start considering some other effects that I didn't mention, like collision and cooling between the gas and the gas. And so we don't know how that will affect the observation, for example, but we know that has effects on some, signal from the planet that is related to something we call buoyancy resonance, or spinal waves driven by buoyancy resonance. But essentially, you change the cooling time scale of your perturbations, and therefore the dynamics can be different because you will respond different to perturbations in the non-LTE than in the LTE regime. Yeah, thanks.
We have a question online from Andrea.
Hi, can you hear me?
Yes.
Yes. Hi. Thank you very much for the nice talk. I have two questions, if I may. One is so when you talk about comparing to observation, and in your model you have massive planets. I mean, more massive than Jupiter. My question is: so this planet, I assume that they are surrounded by circumplanetary disks, which I'm not sure, which are probably in your model. But how do you treat for example, the heating term in a circumplanetary disk come probably from viscosity and from viscous heating when these planets are very young. So how is that included in the model? The second question is, I mean, previous models show that the temperature close to the planet can be very high, above the sublimation temperature of dust. So how do you account for that as well when you calculate your opacities?
Great, thank you. So about the first question, so that's all work in progress that we are. I decide to not include in this talk because it's unpublished results. But indeed, we are looking. So the advantage of these high resolution simulations that we can really model the CPD, I guess, and the distribution of heat as well. So we can include the radiative feedback from the planet as well in the system. And of course, you're right, that's going to change the opacity distribution, and we need to improve our opacity calculations. So some of the opacity calculations are based on the D-sharp model, and where you need to take into account sublimation of gas grains, beyond 160 or 200 Kelvin. So, and that will change the opacity distribution. So one thing we can do is take the monochromatic opacities from the D-sharp and use that as a baseline in our grids to get the mean Rosseland mean opacity, for example, in these systems. This is something we are calibrating as well with other methods, but that's the basic idea. And definitely, I'm excited to show more results about CPDs as well in the summer when we finish with this first part of the project. Yeah. Thank you.
Thanks.
Other questions from either online or in the room? Anybody? have plenty of time, so. Oh, Ilaria has one.
Hi, yeah, can you hear me now?
Yes.
Okay, yeah, thank you very much, Leonardo. This is really, really nice results. I was wondering if you, considering an extra complication is the migration of the planet, how do you think that your results are going to be impacted by the migration?
Yeah, so the time scale of it will depend, of course, of the type of migration that we are looking, but the time scale of these integrations is relatively short in comparison with the migration time scale here. With all this machinery and powerful cluster, we still cannot go beyond 100 orbits. Will be like impossible to reach. But so it will be interesting to see in the future if we can integrate longer time scale and say something about the migration. The point that I want to emphasize about migration is that Pavlov's results suggest that for subthermal or low mass planet machine, the dust component needs to be included to improve our understanding of planet migration. So that's definitely showing we need to explore more with the 3D models that we have.
Thank you.
Okay, well, thank you again for a really interesting talk. And I think that's going to do it for this week's Origin Seminar then. And thanks.
I do have a question.
No, and the question. Go for it.
Hi, Leo.
Hi.
That was very exciting talk. So in these simulations you ran, are there any instances of hydrodynamic instabilities, or are they carefully constructed so they don't have any instabilities?
Yeah. So great. So this all right. So in these simulations, we don't have any hydro instability. So the parameters that we are hydro instability that we know of course, the parameters that we are using are constraining some of the growth of mitigating some of the growth or some instabilities, but something that we are looking forward to look in the future, maybe with you as well, and have some very interesting results now, so we can think about modeling that in this 3D setting as well.
Okay, thank you.
I had a question about the solver itself. So you showed that you can have different meshes and different resolutions. Is it adaptive, or do you need to choose the set plane at the start of your simulation?
It's a static refinement. So you need to set the mesh with a planet mass, and from the planet mass you basically define the resolution that you want in the heliosphere of that planet, and yeah, it's a static refinement. The planet is also fixed here in these meshes.
Any other last minute questions? Okay, so let's thank Leo again.